One of the nice features of C++ is that we have a lot of direct control for how data is stored in memory. This is usually handled within classes, especially in standard library classes, where memory can be managed carefully to give us the memory that we need as we need it. Now, we usually think of the computer's main working memory, the memory stored in RAM, as one uniform block of memory. The items that we declare get space set aside for them ahead of time, and this is known as static memory allocation. It's how standard variables and parameters are stored. But as we start developing more complex objects, sometimes we want to allocate new memory during the program, memory that we didn't know we'd need ahead of time. And that's what dynamic memory allocation is for. Whenever we want to allocate memory dynamically, we also need to understand pointers, which are how we store explicit and dynamic addresses for memory. Let's start by talking a little bit more about the two ways that main working memory gets handled. Here, I'm not talking at all about storage memory for files. Main working memory comes in one of two varieties, the stack or the heap. The names stack and heap come from the way that the underlying data structures work. The stack is static memory that we know and allocate as soon as we declare something. The stack stores all of the variables and parameters. By contrast, the heap is for dynamic memory allocation, for anything that's not known in advance and is instead allocated as needed. The heap is sometimes referred to by a more formal name, the free store. And although we haven't seen a lot of it so far, it's not at all uncommon to be uncertain as to how much memory we'll need. We use dynamic memory allocation whenever we're wanting to store an uncertain amount of information that will keep coming in and thus growing over time. Now, often classes hide this from us. The vector class hides how and where it's allocating new memory. It just gives us functions like pushback to add a new element, and the details of how it gets that memory and adds it on are hidden. But vectors don't always fit the problem that we have. Sometimes we need to allocate memory for ourselves. To allocate memory on the heap in this more dynamic way, we're going to need to get comfortable with a new concept called a pointer. The pointer is just an address in memory, but it can get tricky to use, so pay attention. Let me emphasize this. A pointer is a variable that holds an address in memory. We call it a pointer since it's pointing to some place in memory. It's saying, here's the address where this thing is. Now usually, but not necessarily, there's some data at that point in memory. But remember that the pointer variable doesn't store that data. Instead, it stores the location where that data is. However, a pointer also defines the type of thing that should be found at the address it contains. So, if there's supposed to be an integer at that location in memory, then we'll have a pointer to an int. If there's supposed to be a vending machine at that place in memory, we'll have a pointer to a vending machine. Now, a pointer is declared much like any other variable, but there's some syntax to get used to involving ampersand, asterisk, which we'll read as star, and an arrow written with dash greater than. Okay, to create a pointer, we first list the type of the thing that we're pointing to, but then we also include an asterisk after the type, indicating that this variable is going to contain an address where there's something of that type. The asterisk is commonly read star. So, a pointer to an integer would be an int star. A pointer to a vending machine would be a vending machine star. Once we've declared a pointer, we can assign it a particular memory address. To get the memory address of a variable, we put an ampersand in front of the variable's name. You can think of the memory address as being like GPS coordinates. In our code example, if we've declared a variable, current machine, that's a pointer to a vending machine star, and a vending machine object, like the lobby vending machine, then we can assign the address of that particular vending machine, the lobby vending machine, to that pointer by writing current machine gets ampersand lobby machine. That means that the current machine will then contain the memory address of lobby machine. We can also think of the memory address current machine as a reference to lobby machine. Now, once we have a pointer declared and we've assigned a memory address, we can get the thing that it's pointing to. That is, the thing that's at that memory address. Getting the thing in memory is known as dereferencing the pointer. And there are a couple of ways that we can do this. The most basic way to dereference pointers is to use the asterisk or star in front of the pointer name. So in the code you see here, we create an integer x that gets assigned the value 3. This integer is a static variable. Then we create a new variable, y, that is a pointer to an integer. The pointer is not set to anything initially. We assign y the address of x. So y gets the address of x. So we now say that y points to x. The variable y contains x's address. When we output star y, then we're outputting the value that y is pointing to. In this case, that's the integer that it's pointing to, and it has the value 3. So we output 3. In the next line, we're assigning a value 5 to the integer pointed to by y. So the memory location that y is pointing to will get the value 5. This is the same memory location that's being used by x. So when we then print out the value of x, we see that x has the value 5. So that's how we use an asterisk to dereference a pointer. Another way we can dereference a pointer and get the thing in memory is to use an array operator and access element 0. The reason this works is that an array is actually a pointer. The array variable holds the address where the first item of the array is stored. When we write sub0, we're getting the value stored at the place that the pointer is referring to. And if we write sub1, we mean the thing stored one position in memory past the place that the pointer is referring to. So the code you see here works identically to the previous code. The only difference is that instead of writing star y, we write y sub 0. Now, if we have a pointer to an object, but only to an object, there's a third way that we can dereference pointers. What we can do is access public member variables or public member functions by using a minus sign followed by a greater than sign. And if you look at it, that looks kind of like an arrow. So it's known as the arrow operation, even though it's not really an arrow. This is the same as if we dereferenced the pointer and then used the dot to access the member variable or function. Here's an example. We have a very simple class called hero that consists of two public member variables, name and characteristic, and that's it. In our main code, we declare a hero variable h, and we set the value of the name to be Hercules and the value of characteristic to be strength. And we then create a pointer to a hero named laboring hero, and we set that pointer to be a reference to h. In other words, we give the pointer laboring hero a reference to the hero h. So now, if we output laboring hero arrow name and laboring hero arrow characteristic, we see that the values are Hercules and strength. And this is the exact same thing that we get if we were outputting star laboring hero dot name and star laboring hero dot characteristic. Now that we have pointers, we can start to perform dynamic memory allocation. Remember what we said earlier about the heap and the stack? The stack holds all of the variables that we declare and those that we pass as parameters. And the heap holds data that we don't know ahead of time, but we allocate during execution. Memory is allocated or deallocated on the heap only when we say to. The new command creates a new object on the heap, and it returns a pointer to that new object. So to use the new command, we just write new, followed by the type that we want to allocate. If there's a second constructor defined in addition to the default constructor, we can invoke it by putting parentheses afterward with the arguments that we want to pass to the second constructor in the parentheses. Here's an example. In this case, we have our class named Hero with two public member variables, name and characteristic. We've also defined two constructors. The first is a default constructor that sets the name to John Doe and the characteristic to nothing. And the second is a constructor that takes in two string values that it uses to initialize name and characteristic. Now, in our main routine, we've declared two pointers to heroes, h1 and h2. The pointer h1 is assigned the result of new hero. What this does is it allocates a hero in the heap's memory, and then it calls the default constructor on that hero. The result is the address of that location that was just allocated. This address is then assigned to h1. Likewise, we assign h2 the result of new hero parenthesis Hercules comma strength parenthesis. Now what happens here is that new allocates memory on the heap to store a hero. It calls the constructor of the hero class that takes in two string parameters, and then it returns the address of that newly created hero, and this gets assigned to h2. So when we print out the values of name and characteristic in h1 by outputting h1 arrow name and h1 arrow characteristic, we see John Doe and nothing. And when we print out the values of name and characteristic in h2, we see that they're Hercules and strength. If we want to allocate several of an object, we allocate an array on the heap. When we allocate an array, then after the variable name, we just put brackets with the size of the array that we want inside. So, if we have a pointer to a hero named H, and we want an array of 10 heroes, we can assign H the result of new hero bracket 10 bracket. And this will create an array of 10 heroes. And we can then access individual elements like h sub 3.name, which would be the name member variable of the fourth element of the array. When the array form of new is used, the default constructor is called for each of the elements. Now, I mentioned before that data stays on the heap until it's explicitly deallocated. Once we're done with whatever memory we allocated, we need to explicitly free it. Now, unlike the stack memory that's automatically freed when a function call completes, the heap memory stays allocated until the end of the program unless we free it. So, to free memory on the heap, we use the delete command. We just write delete and give a pointer to the thing that we're wanting to delete. And the allocated object will then be deleted from memory. So, if we allocated an array, we have to instead write delete brackets to delete the entire array that was allocated. One other thing that's useful when setting up a default variable is a null pointer. Sometimes we have a pointer, but we don't want it to point to anything in particular. We just have it to use sometime later. And in this case, we can set the pointer value to be the value null. The null pointer does not point to any usable memory location, but it functions as a special value that we can have the program check when no value is what's needed. We'll see a way that this is used in the program that we'll develop in a couple of minutes. Pointers are notorious for how many errors they can cause in programs. And a common problem with pointers goes like this. We allocate memory with new, and we give the result to a pointer. There's now a chunk of memory allocated on the heap. So far, so good. But then we do the same thing again, assigning to the same pointer. So what happens? The reference to that first thing that was allocated is totally lost, but the memory stays allocated. It's using up the computer's memory, and there's no way to get rid of it. And we call this a memory leak. Now, multiple pointers are often a recipe for problems. They might be pointing to the same thing, and one of the pointers might accidentally modify something that you didn't intend to. Or one pointer might be pointing to some object when another pointer deletes it. And so in the end, you're left with pointers pointing at a space in memory that's now free and could have anything in it. Pointer errors can be easy to make and really difficult to find when debugging. And yet, there are cases when we do need to use pointers. When we're reading in an unknown amount of data, or when we need a lot of memory, but the operating system, as it often does, has limited the amount that can be used on the stack, then we need to use dynamically allocated memory. For the example, I'm going to show you how to create a 20 questions type of game. This is a game where you ask someone up to 20 true-false questions to try to guess what they're thinking of. For our game, we'll want to create a tree structure where every internal node is a question, such as, is it alive? And if the answer is true, we'll head down one side of the hierarchy, and if the answer is false, we'll head down the other. Now to do this, I'm going to introduce a way to generate a special tree known as a binary tree. This is a tree where every node has at most 2 children. Each of the leaf nodes in our game tree is going to be a guess. It's the thing that we hope the person is thinking of. Now for our game, if our program guesses wrong and thereby loses, then the program will ask the person playing to volunteer a question that teaches us how to distinguish our guess from their item. And that will let our game learn so that it can play better the next time. We'll create a new question node, which will allocate on the heap, and another new node for the new guess. And that is, the previous wrong guess will be one child, and the new item will be the other child of the question node. As an example, for playing the game, we might first ask, is it alive? If the answer is no, then we ask, can you hold it in your hand? And if the answer is yes, then we might guess, is it a rock? And if that's not the right answer, and the right answer was a pencil, we would then ask the user, what is a question to distinguish a rock from a pencil? And then we'll use the question, which might be, do you use it to write, to update the tree. Okay, I'll walk through the process here. We have a class named node, since each object that we create will be one node of the tree. The node is going to have 4 member variables. The first of these is a Boolean, is answer. And that will be true if the node is an answer node, and false if it's a question node. Next, we'll have a string named text. For an answer node, this will be the thing that we're going to guess. For a question node, it will be the question that we want to distinguish between the 2 items. And finally, we'll have 2 pointers to more nodes. We'll have a pointer to the false answer and a pointer to the true answer. So for a question node, one of these will be a pointer to the node that we should go to next if the answer to the question is yes, and the other will be the one to go to if the answer is no. We'll create 2 constructors. The default constructor will create an answer node with the text rock. So it'll set isAnswer to true and the text to rock. And both the false answer pointer and the true answer pointer will be set to null. This is an answer node, so there are no children and therefore nothing to point to. The second constructor will take in a string as a parameter. It'll again create an answer node so that isAnswer is true and both pointers are null. The main part of the class will be the askQuestionMember function. This is going to be the function to call to have the computer ask the question in that node, either trying to guess the answer or asking a question to narrow down choices. The askQuestion function will return true if the computer wins the game. The function will guess the answer, or return false if it doesn't win the game. The function will have two parts. One option if it's a node with a final guess, and one if it's a node to ask another question. So let's look at each one separately. If it's a node with a final guess, then we'll make a guess of what we think the player is thinking of. We output our guess asking, is it a whatever, where the guess is the text member variable. We then read an answer from the user. If the answer is yes, it means we guessed the right thing, and so we just return true. The game's over, hooray! On the other hand, if our guess was not correct, we need to update our decision tree. So we first find out what item the person was thinking of, and this is going to become a new answer node. We next ask the user to give us a question to distinguish our incorrect guess from the thing that they were thinking of. This question gets read in as an entire line since it's not just one word. We use the getLine command to read the question in. Remember from way back in lecture 9 that getLine handles carriage returns a weird way, in that it first reads any leftover carriage return that might have come after streaming in a variable as an entire line. So we have to call getLine twice. Once to get the new line that came from pressing enter after typing the name of the thing that the user was thinking of, and then another line will read in the entire thing that the user wrote. Okay. Following this, we're going to create two new children nodes. Both of these will be answer nodes. We'll use the new command to create a new node using the constructor to give the answer text to use for each. So the new command allocates a new node on the heap, and the constructor initializes that node appropriately. One of the nodes will have the new item as an answer. The other node will have the existing answer. And then finally, we update the current node. So instead of this node being an answer node, now it's going to be a question node. So we change the text to be the question that we just read in, and we set isAnswer to false. That designates that it's now a question node. Now, that can be used to ask a question, and we'll go to one of the two answer nodes, either the new one that we just learned about, or the answer that we had previously in this node. So, next time we play the game, instead of guessing the wrong answer, we'll instead ask a question to distinguish between the two different answers. And finally, we return false. We did not guess the thing that the person was thinking of, so we did not win the game. On the other hand, we also need to handle the case where we have a question node. In this case, the operation is relatively simple. We print out the question, and we get a yes or no answer from the user. If the user answered yes, then we call askQuestion on the node pointed to by the true answer pointer. Otherwise, we call askQuestion on the node pointed to by the false answer pointer. In either case, we just return whatever the result of that node is. Basically, we go down to the next level of the tree and again ask a question there, either making a guess if it's an answer node or asking another question if it's a question node. And this will continue until we eventually reach a leaf of the tree where we'll have an answer node. Now, this final operation is a pretty straightforward example of what's called recursion. Recursion refers to a function calling itself. In this case, the member function askQuestion was calling askQuestion again, though this time on a different node. The point here is that once we're at a node, we treat the remaining tree just like we would the original tree. In other words, for any one question node, the subtrees are themselves trees. Okay, back to our program. The only thing left is the main program that actually runs our game. So, we start the game by creating a node with the default constructor named firstNode. And remember that this will create an answer node with the guess rock. So, the game will always start the first time with the computer guessing that the user is thinking of a rock. Then, we'll repeatedly ask the user if they want to play the game, and as long as they keep answering yes, we play another round. Each time to play the game, we just call askQuestion on firstNode. And depending on whether we get a true or a false returned, we either celebrate winning the game or we sulk that we've lost. If we run through a few games, we can see this work. The first time through, we think of a pencil if we're playing as the user. We're asked if it's a rock, and after giving no for an answer, we get to input a question to distinguish a pencil from a rock. Can you write with it? Now remember that what happens here is that we create two new nodes on the heap, one for the rock answer and one for the pencil answer. And we change the current node to be a question node. So at this point, we'll have one question node and two answer nodes in our tree. We can keep playing, and the more we play, assuming the computer doesn't win, the bigger and bigger the tree will get. That is, the more our program will learn. And in principle, we can go until the computer runs out of memory. Now in practice, the computer will eventually win or will run out of time to play, but you get the idea. Dynamic allocation of memory gives us the potential to expand without limit. But memory is never unlimited, and this leads to another aspect of object-oriented programming, the destructor. Destructors are special functions called when it's time for an object to be removed from memory. The destructor function is meant to clean up when it's time to get rid of an object. In code, a destructor is declared just like the special constructor functions that we saw last lecture, except that a destructor starts with a tilde. Tilde was an old symbol in formal logic to show negation, so now it's used to designate the negative of a constructor. After the tilde comes the class name and parentheses with no parameters. In particular, the destructor is the place to delete previously allocated dynamic memory. For example, our 20 questions program keeps all the memory we allocated around until the end of the program. Is that okay? Well, one person probably won't play long enough for the computer's main memory to be used up. But suppose that same program becomes available as a public demonstration. It's always good practice to free up any allocated memory in the same object that created it. What that means is, when it's time to delete a node, we also need to delete its children branches. So, we ought to define a destructor in this case. The destructor will only need to call delete on the children if it's a question node, since answer nodes don't have any children. So, we first check to see if it's a question node. If so, we call delete on each of the children. The destructor will then be called on those nodes, and they'll call the destructors on their children, and so on all the way through the tree. Okay, lastly, I want to point out a partial alternative to the trickiness of dynamic memory allocation. That's using vectors. Vectors are a way of indirectly allocating data on the heap, without you yourself having to use pointers or the allocating and destructor commands for new and delete. All that work is hidden inside the vector class. Now what happens when a vector is first created is that there's enough space allocated on the heap to hold all the data in the initialization plus a little bit more. And as you keep adding elements onto a vector, eventually the memory that was allocated gets used up. The extra gets taken up by the elements being pushed on. But when the vector is finally full, when it's used all the memory that was already allocated, then it goes through a process to get more. It allocates double the amount of memory, and then it copies all of the old data into this new memory, and it deletes the old memory. So now it has twice as much memory to work with, so it should take even longer before that memory fills up. And this can keep going as long as more data keeps being added to a vector. Vectors have been known to have 1 million elements in them. I've written some of those myself. So if you find yourself wondering, should I use a vector or should I write my own dynamic memory allocation, then use the vector. With a vector, you're still using the heap, but it's a little easier to use and you're much less likely to run into major errors or the other problems that people tend to encounter when using pointers. The advantage of dynamic memory allocation with pointers, and the reason you should remember them, is that you can have situations like our 20 questions game, where the data that you need to allocate doesn't fall neatly into a vector structure or any other standard library structure. And anybody writing system software or direct interaction with devices will need to use dynamic memory and pointers even more, since direct interaction with memory is what operating systems and device drivers do. Dynamic memory allocation has its pros and cons, but sometimes it's the only way to get things done. Dynamic memory allocation is also something you need to keep in mind if you need to allocate an amount of memory that you can't predict ahead of time, or if the memory has a special structure like the binary tree that we used in the 20 questions game. Thanks to classes like vectors, beginning programmers need to use dynamic memory allocation less and less frequently. But it's important to understand if you want to know how C++ is working under the hood on your behalf. When you understand dynamic memory allocation, that makes you a better user of C++, even if your own programs rarely make direct use of the pointers, new and delete. In the next lesson, we'll get to learn about a way of potentially saving lots and lots of programming work through inheritance. See you then.